Welcome to this video about biomechanics, where we're going to be talking about force reduction methods. In a previous video, we considered an example problem where we had a person doing a simple leg lift, and we drew a free body diagram for the knee, or for the lower leg, and we considered the forces at the knee. We made a really important simplifying assumption when we assumed that there was a force in the x direction at the knee, a force in the y direction at the knee, and a moment about the knee. That's a really useful way to go about reducing this to a problem that we can solve, but it has significant limitations in that it doesn't actually tell us anything about what's going on in the muscle or tendon or ligament tissue. So it doesn't tell us anything about the forces that the tissue itself is experiencing. The assumptions that we make when we solve a problem, when we just set up a problem, define the usefulness of the question that we can ask with that model. And they define the usefulness of the results that we get out. So while this is a good general assumption that does provide some information about what's going on at the knee and is a technique that we use frequently throughout biomechanics to just look at the internal moments and loads, it is limited when we start to ask questions about particular tissues and the loads that they're carrying. The challenge that we run into, though, and the reason that we do this, is that most biomechanics problems are statically indeterminate, at least anatomically speaking. There are more muscles present and active than there are equilibrium equations, because if you remember, for a 2D planar situation, there's only 3 equilibrium equations. Some of the forces in the x, some of the forces in the y, and some of the moments. Okay, it gets more complicated. You get more equations if you go into 3 dimensions, but then you have more forces and more components to be considering too. So we need a way to simplify that, and this internal forces at the joint was one way that we use that's very common that we use to tell us some information about the motion and how that's affecting the body. But there are a couple more ways that we can use in order to try and get information about the forces themselves. So here are 4 methods that we're going to talk about to get more useful information. 1, force reduction. 2, muscle scaling. 3, soft tissue deformations, relationships. And 4, performance criteria and mathematical optimization using performance criteria. So we're going to take a look at each of those 4 things in the next few minutes. So let's consider the first method, force reduction. If you set enough individual forces equal to 0, you can reduce the number of unknowns that you have to match the number of equations. That's good if you have one muscle that dominates, or if you have muscles that all insert at the same point. And therefore, you can reduce them or replace them with a single force acting at that point. A couple of examples of this are the quadriceps, where you've got 4 muscles, and the erector spinae, where you've got a lot of muscles that all insert at roughly the same place on the spine. So these are both examples of places where you could replace the muscles with the group of muscles with a single force or a single force that model the whole group of muscles. Again, it limits your question. You can't tell anything about the individual muscle bundles, but it gives you a way to solve the problem mathematically and tell you something about what the forces are doing. So you can check this assumption by using EMG, which we'll talk about more later. But there's a major assumption here that you need to be aware of, and that is that forces being 0 means that those muscles aren't active. So we're making the assumption that only the muscle that we're interested in, that we've modeled, is active, that the other ones are not active at all. This is good and allows us to solve the problems mathematically, as you'll see with the quadriceps tendon in the example on the next video, and also as you try and do it in your homework. But it is limited in what information it gives you. The second method that we're going to talk about is muscle scaling. Virtually all skeletal muscle tissue can sustain a maximum stress of about 0.2 megapascals, which means that the force to area ratio, stress is force over area, is constant for that tissue. That's super useful because we can write an equation for each muscle where we take the total area of the muscles, the total force generated at the knee, and use the ratio of the area of the muscle to the total area and the forces to provide an extra equation for every muscle in the model. So this gives us an extra equation for every single muscle in our model, which is good. It increases the number of equations that we need to solve, but it gives us more equations for our unknowns, for our statically indeterminate problem. The assumption that we're making here is that all muscles are equally active. So in our force reduction method, we assumed that some of the muscles were not active at all. Here we're assuming that all of the muscles are equally active, which again has implications for our conclusions. The other thing to note, caveat, is that the cross-sectional area of the muscle is hard to measure. So typically we use something called the physiological cross-sectional area, which is the volume of the muscle divided by the length of the muscle. Physiological cross-sectional area, PCSA. And that gives us the area of the muscle that we use instead of trying to measure the cross-sectional area or figure out which point along the muscle, if the cross-section changes along the length of the muscle. It gives us a constant, consistent thing to use. The third method that we can use is a soft tissue force deformation relationship. So you remember from your physics classes or your material science classes that there's a relationship between the stress and the strain for a material. Well, if you know this relationship, if you know the material properties of the tendon or the ligament, for example, the Young's modulus, and you can measure the deformation of the tissue, then you can use the stress-strain relationship, Hooke's law, over here on the graph, to estimate force. Since you know the relationship between stress and cross-sectional area and force, you can use the physiological cross-sectional area, the PSCA, again, to measure that. So that's a really good idea in theory. That's great, right? It's a super nice way to do this, but the challenge is that you have a tendon, a muscle, and it's covered by skin. So it's really difficult to measure the deformation of this tendon. This is the Achilles tendon here. It's really difficult to measure how much this deforms as you move, the deflection, because it's covered by the skin. So if you have ways around that, you can get that information. If you're working with a cadaver model, for some reason, you could get that information, but it doesn't necessarily do us a lot of good in live subject biomechanics because there's a significant limitation. Now, there are a lot, that is actually an ongoing area of research in biomechanics right now. There's a lot of really cool work being done with ultrasound transducers, trying to measure both the deformation and using a technique called shear wave elastography to estimate the material properties of the tendon, so you don't just have to go with the table says the modulus is, but you can actually measure the elastic modulus of the tendon using the speed of a shear wave traveling through the tendon. It's really cool stuff. Shear wave elastography, and then tracking using ultrasound to measure the properties of the tendon. So if you want a cool article aside to go investigate, check out shear wave elastography and tendons. The fourth technique that you can use is performance criteria via mathematical optimization, where you add performance criterion to specify a unique set of forces among load-carrying elements, and then use mathematical optimization. So basically, this is a math technique where you optimize for a solution, and it doesn't require determinacy. So it removes the static determinacy constraint. You can have more equations than you have unknowns because you're looking for some sort of optimum point, right? Remember back to calculus where you found the minimums of functions or the maximums of functions or the inflection points of functions, those kinds of things. So to do this, you start by creating a cost function. So for example, maybe the total stress. If you have two muscles, muscle 1 or tendon 1 and tendon 2, applying a load to something, to maybe the arm here, you have 1, and you have 2, and each of those has a stress. So this is your cost function, sigma 1 plus sigma 2. Then you take that and you use a solver to optimize based on some criterion. So one criterion that the body commonly uses is to minimize the total stress, or at least we think that the body commonly uses is to minimize the total stress. There are a lot of other really cool optimization ideas out there, but this is a simple one that is pretty easy to implement. And then finally, you go ahead and solve using some sort of solver, MATLAB, MathCAD, something like that, where you're minimizing your cost function. So this is in addition to your static equilibrium equation. So you're going to include your sum of the forces, your sum of the moments, and your minimization function in your solve block in MathCAD or in MATLAB. So this is a brief overview of the different kinds of ways that you can do optimization in order to reduce the number of unknowns or to solve for more unknowns than you have equations in a biomechanics problem. You're going to dig into a couple of these methods on the homework. There's an example video of the knee problem that's next up. And as always, bring your questions to class. I'll see you there.